So now that we have learned all about confidence intervals, I want to introduce you to hypothesis testing for proportion. So just like I did with confidence intervals, we'll sort of end with the actual hypothesis test. I want to talk about all of the parts before we actually do the test. So what we did previously with confidence intervals is we created an interval that we felt confident contained the population proportion. And now what we're going to do is, instead of creating an interval, we're going to say, would it be possible, based on our collected or sampled data, that some value is true? So what we're going to do is basically we're looking at the data, and if the data that we find in our sample are consistent with the model, then we're going to believe that the hypothesis is true. So let's say I hypothesized a value of 13% and my sampled value was 13.5%. That's really, really close, so it's probably okay. But let's say I hypothesized a value of 13% and I found a value of 50%. Well, now I'm feeling like maybe that hypothesized value is not okay, and therefore I'm going to reject the model. So this is really the hardest thing right here about hypothesis testing. So most people do really well on all of it, but then they really struggle with what happens when they get to their p-value. So essentially what I'm saying is I am going to find something called a p-value. And a p-value is a conditional probability. So we've talked about conditional probability, that something happens assuming something else already happens. So what I'm going to do is find the probability that the event I've witnessed, or one more extreme, so even higher or even lower depending on the situation, could happen given that the proposed hypothesis is true. So given the hypothesis is true, how likely is it that I would find a sample like I did? And that is called a p-value. Again, using that example from before, let's say my hypothesized value is that p is 0.13. And then my observed value, and again, there's a lot of calculations that go with this, but we're just trying to make it simple for right now. Let's say my observed value is 0.135. Well, that's pretty darn close, and therefore I'm going to say, yes, the null hypothesis is probably correct. But I can't say it's correct. I'm basically saying I don't have enough to say it's not correct, and so I'm going to fail to reject the null. And don't worry about the word null. We'll talk about that in a little bit. Basically, I'm going to fail to reject that the hypothesis is 0.13, which essentially is me saying, I think that hypothesis is probably right. Now, if I get a p-hat that's, say, 50%, so 0.5. And again, I haven't talked about that in terms of p-values yet, but if I get a p-hat of 0.5, my p-value is going to be really, really low, which means it's not likely I find a p-hat of 50% if it's true that p is 0.13. Therefore, I'm going to reject the hypothesis. I'm going to say, this must be wrong because I found a value of 50%. So again, I want to give you a little bit of a preview as to what we can expect with hypothesis testing. And there's quite a few different steps that we're going to obviously go through together. But for now, we're just going to look at the meat and potatoes of it. And this example says the cracking rate of casts in a steel mill is believed to be 20%. Recently, a test of 400 casts produced 17% cracked. Is the new crack rate lower crack rate? Is the new crack rate lower? Man, I'm just falling all over myself. Due to a new engineering process, or is our sample by random chance? So we're going to talk in the next video about where to come up with these hypotheses. But my null hypothesis is always going to be that nothing has changed. So I'm going to write it in words. We expect the crack rate to be 20%. Why? Because it's believed to be 20%, and I'm always going to assume that nothing has changed. So notice my null hypothesis is 20%. Then I have my alternative hypothesis, which is always based on the context. And this one says, is the new crack rate lower due to the new engineering process or by random chance? So lower tells me specifically that I want less than or equal to 20. So again, when I do this, I'm going to look at a z-score, and z-scores we're super familiar with. We've done them a lot. Z is observed minus expected over the standard deviation, and my observed value was the 17% cracked out of 400. My expected value was the 20%. And notice here I'm using standard deviation, not standard error. So I'm going to actually use the p, which is the value that I assume is still going to remain true. And when I do all of that, I get a z-score of negative 1.5. And then what I want to do is go into StatCrunch and use my normal calculator, which I'll review with you in a little bit. And when I do that, I get 0.067. And here's what that means. Assuming that the true crack rate is 20%, I can expect to find a sample of 17% or less about 6.7% of the time. That's where this comes in, 6.7% of the time. So again, what does that tell me? Well, if the p-value is 1%, it's extremely likely it didn't happen by chance. If the p-value is 90%, we're assuming it just happened by random chance. So what does 6.7% mean? Well, we have to talk more about p-values and alpha levels to determine if we can say that it is in fact a lower rate or if it just happened by chance.